Right now, a bolt of electricity, 5 times hotter than the surface of the sun, is tearing through the air at 200,000 miles per hour. We see it 40 times every single second across the globe. We've harnessed the atom, we've mapped the genome, and we've sent probes to the edge of the solar system. But here is the humiliating truth. Science still doesn't actually know how that bolt began. We are looking at a fundamental mystery of the universe that happens in our own backyard, yet defies the very laws of physics we wrote to explain it. Welcome to Deep Science Explained. Lightning is the most common high-energy event on Earth, a bridge between the heavens and the earth. We've been told the story since elementary school. Clouds rub together, static builds up, and pop a spark flies. But when physicists actually fly planes into thunderstorms to measure the electric fields, they find something impossible. The fields aren't strong enough. According to standard electrostatics, lightning shouldn't be able to strike. It's a paradox that has haunted researchers for centuries. Today, we are venturing into the heart of the storm. We will explore the hidden cosmic connection to our weather, the terrifying phenomenon of dark lightning, and the deep science of how a tiny ice crystal might hold the key to a planetary-scale explosion. This isn't just a weather report. This is a journey into the breakdown of reality itself. To understand why lightning is so mysterious, we have to look at the dielectric breakdown of air. Air is a fantastic insulator. It hates letting electricity pass through it. To force a spark across a gap of air, you need a massive amount of voltage, roughly 3 million volts per meter. Imagine a thunderstorm 6 miles high. To get a bolt to jump from the cloud to the ground using basic physics, the cloud would need to hold an electric field so powerful it would practically glow. But here's where it gets crazy. When we send weather balloons and sensor-laden jets directly into the most violent supercells, we only find about 1/10 of the required strength. It's like trying to start a fire with a single lukewarm ember. By all rights, the lightning should never happen. The static friction model we learned in school is woefully incomplete. So how does the air break? The leading theory involves a beautiful chaotic dance called the Grapple effect. Inside a storm, millions of tiny ice crystals rise, while heavier, slushy pellets called grapple fall. They collide. In that collision, electrons are traded. The top of the cloud becomes positively charged. The bottom becomes a jagged reservoir of negative energy. But even charge separation doesn't explain the initiation. We need a bridge across the insulation of the air. This is where we look into the microscopic world of hydrometeors. Imagine a single jagged snowflake or a droplet of water being pulled by these immense electric forces. As the force increases, the water droplet doesn't stay round. It stretches into a sharp, needle-like shape called a Taylor cone. From the tips of these needles, tiny jets of ionized plasma begin to leak. These are called streamers. On their own, they are weak, but they act like a trail of breadcrumbs in the dark. Deep Science Explained, researchers have found that these streamers can create a localized hotspot where the air finally loses its grip on its electrons. But even these jets are often too small to bridge the gap of a mile-long sky. There is a missing piece of the puzzle, a ghost in the machinery of the storm that suggests our atmosphere isn't a closed system. Did you know that a single lightning bolt can contain enough energy to toast 100,000 slices of bread? But even with all that potential, we still lack the trigger. Some scientists at Deep Science Explained suspect the trigger doesn't come from the cloud at all. It might come from across the galaxy. This is the runaway breakdown theory. It suggests that high-energy cosmic rays, remnants of exploded stars from millions of light years away, collide with our atmosphere. These rays strip electrons off air molecules, creating a seed of ionized air. These electrons are moving so fast that they don't get captured by other atoms. Instead, they smash into them, creating an avalanche of trillions of electrons. This seed creates a conductive path, a needle threading the cosmic eye, allowing the lightning to finally rip through the sky. Think about the scale of that. Every time you see a flash of light during a summer storm, you might be witnessing the direct result of a star dying on the other side of the universe. We are literally connected to the deep cosmos through our rain clouds. But wait, it gets stranger. There is a hidden side to the storm that your eyes can't see. It's called dark lightning. High above the clouds, thunderstorms launch bursts of terrestrial gamma-ray flashes, TGFs. the most energetic form of light in the universe, into space. These are the same rays produced by nuclear explosions and black holes. You could be standing under a storm, unaware that a natural particle accelerator is firing over your head, leaking the secrets of quantum mechanics into the upper atmosphere. When a pilot flies near a storm, they might be hit by a dark lightning bolt that provides a radiation dose equivalent to a full-body CT scan in a fraction of a second. This isn't just weather, it's a high-energy physics experiment running on a planetary scale. This brings us to the big discovery. Lightning doesn't just fall, it's an intricate two-way conversation. It begins with steppe leaders, invisible rivers of plasma that stumble down from the cloud in 50-meter chunks. They are searching. They are feelers reaching into the dark. They don't move smoothly. They step, pausing for a microsecond to gather energy before leaping again. As the leader approaches the ground, the earth feels it. The electric field on the ground becomes so intense that the ground becomes desperate to bridge the gap and reaches back. Objects on the surface, trees, lightning rods, even the blades of grass begin to launch positive streamers upward. These are faint, violet fingers of electricity clawing toward the sky. Science explains simply, the lightning bolt you see is actually the return stroke. It's the moment the connection is made and the circuit is closed. The sky doesn't just hit the earth meets the sky halfway. It's an analogy for life itself, a desperate search for connection through a hostile medium, ending in a transcendent release of energy. As the leader and the streamer meet, a tunnel of ionized gas, or plasma, is formed. This tunnel is only about an inch wide, but it is a perfect conductor. The sudden surge of current causes the air to expand at supersonic speeds, creating the shockwave we hear as thunder. But what happens inside that tunnel? This is where the mystery of the universe gets even deeper. At the moment of the strike, the pressure is so great that it can actually trigger nuclear fusion. Scientists have detected isotopes of nitrogen and oxygen that can only be created by nuclear reactions inside a lightning bolt. This means that every storm is a series of tiny, fleeting nuclear reactors going off around us. We aren't just seeing electricity, we are seeing the transmutation of elements. As the philosopher and scientist Nikola Tesla once said, if you want to find the secrets of the universe, think in terms of energy, frequency, and vibration. In the heart of a lightning bolt, we see all three. We see the vibration of molecules turned into plasma, the frequency of the pulse, and the raw energy of the mystery of the universe. Tesla believed he could harness this atmospheric energy to power the world for free. He saw the Earth and the ionosphere as two plates of a giant capacitor. While he never fully realized his dream, modern deep science-explained research suggests he wasn't far off. The Earth is constantly being recharged by about 2,000 thunderstorms occurring at any given moment. Without this constant bombardment of lightning, our planet's electrical balance would collapse, and the very chemistry of our atmosphere would change. We must also consider the ball lightning anomaly. For centuries, people have reported seeing floating orbs of light during storms, spheres of electricity that can drift through closed windows, hover in the air, and then vanish with a bang. For a long time, science dismissed these as hallucinations. But in 2012, researchers in China captured ball lightning on a high-speed spectrograph. They found it contained the same elements as the soil: silicon, iron, and calcium. One theory is that when lightning hits the ground, it vaporizes the soil, creating a cloud of silicon nanoparticles that burn slowly in the air. But even this doesn't explain how these orbs can pass through solid walls. It suggests there are states of matter and electromagnetic configurations we still don't understand. So why can't science fully explain it? Because lightning sits at the intersection of everything. It's meteorology, it's electrostatics, it's quantum mechanics, and it's cosmic scale astronomy. It's a reminder that even the most common sights in our lives are often the most profound. We live on a planet that is essentially a giant self-charging battery, spinning through a vacuum, being pelted by stardust that triggers violet explosions in our sky. We are observers of a phenomenon that is as old as the planet itself, yet every strike is a unique, chaotic event that resists being boxed into a simple equation. What if reality itself isn't what we think? What if the storm isn't just weather, but a biological-like system the Earth uses to balance its energy with the cosmos? Next time the sky turns gray and the air begins to hum with ozone, don't just look at the light, listen to the silence before the crack. You are standing in the middle of a laboratory that spans the entire universe. Perhaps lightning is the way the universe reminds us that the vacuum of space is not empty, but filled with a hidden architecture of energy that we are only beginning to map. We are the children of the spark, living on a world held together by the very forces that occasionally rip the sky apart. I'm your host, and this has been Deep Science Explained. If this spark of knowledge moved you, hit the like button and subscribe. Let's keep chasing the light together. In our next episode, we'll uncover something even stranger: the ball lightning anomaly, the glowing orbs that can pass through solid walls and vanish without a trace. We will look at the fringe theories of quantum macroscopic states and whether these orbs are a bridge to a different kind of physics altogether. Stay curious, because the more we know, the more we realize how much is still hidden in the dark.